Thank you very much. Let's see if this goes. There we go. All right, thank you very much. And today you're going to hear a lot of talks about the Sun-Earth system. And a theme that goes through most, if not all of them, is that of magnetic fields. And that's because magnetism lies at the heart of many of the mysteries of solar terrestrial science. It crosses the boundaries of time and space, from space weather to space climate, from the sun to the Earth. And there's something about magnetism that's at the same time familiar and yet exotic. There's definitely an element of magic or fantasy in it, which is why perhaps the first time we come across it is in fantasy, in comic books, for example. And what I wanted to point out in this slide, do I have a pointer up here? There we go. Is that in the comics, magnetism is a force that can be controlled by the superhero or by the supervillain. And as you can see, it's helpfully telling us that Magneto is not a hero. But magnetism is very real and something we experience in our daily life. And indeed, it's something that humans have been experiencing since there have been humans, because there exist in nature naturally occurring magnets or lodestones, which attract iron, for example. And in fact, one of the first statements about a magnet, written statements about magnets, and one of the first statements, perhaps, of natural philosophy was made by the Greek philosopher Thales of Miletus. And he said, "The magnet is alive." And this is actually a really interesting statement, because what this means, and it's sometimes translated as, the magnet has a soul. What this means is that the magnet itself is exerting as a force, is causing the iron to come to it. And this is very different than, for instance, saying that the god is making the iron move to the magnet. The magnet itself is exerting a force. So the magnet is alive. Now, of course, in human history, we began to realize something else, which is that the magnet is useful. And compasses have been around for a long time, originally used in fortune-telling, essentially, but eventually used in navigation, and of course are incredibly useful for navigation. And that was by about the 12th century that was happening. Now, fast forward to the 21st century, and I think there are dozens, at least dozens, of magnetic hard drives in this room right now, with all of the various cell phones and devices. Yeah, we can do a count. They're everywhere. And of course, we depend on magnetism for our technology, our MRIs for medical research, for example. So the magnet is useful. But the magnet also can be dangerous. This is a nice image of somebody just holding a magnet up to a television screen on which is projected a picture of a clock. So it's a force that can be disruptive. So magnetism is all around us at home, but it's all around us in the universe as well. And these images are all examples of processes, dynamic processes that have been linked to magnetic fields, and more particularly to the concept of the storage, the slow buildup of magnetic energy and sudden explosive release. And today you'll hear many talks about solar system examples of this: coronal mass ejection, magnetic fields of the Earth's magnetosphere being stretched back and causing magnetospheric substorms, prominence eruptions associated with coronal mass ejections. And there'll be more about that from me and others today. But if we look at other stars, this is an artist's conception of Evie Lacerte, and this was an observation taken by the Swift X-ray telescope of a stellar flare. And this star is small relative to our sun. It's about 1% of the sun's light, about a third of its mass. And yet this stellar flare was thousands of times stronger than any solar flare that we've ever observed. And the reason for this has to do with the fact that this is a young, fast-rotating star, which presumably can build up more magnetic energy to drive the flare. This is an even more exotic object. This is BL Lacerte, again an artist's conception. This is a supermassive black hole at the heart of an active galaxy. And this is a particular blazer which was observed to have a relativistic jet pointing at the Earth. And the theory behind that, again, is magnetic fields that twist up and drive a shock, and so this jet. This picture is a little bit more down to earth. This is actually a photograph of a laboratory experiment at Caltech, the so-called spider leg formation. These are plasma-filled protons and electron magnetized tubes which come together and coalesce and build up energy. And a microsecond after this particular picture was taken, a beam of plasma came out the middle. And at the heart of all of these, this is a representation of magnetic fields. And these are magnetic field lines, which are essentially telling you the path that the magnetic field takes and the plasma takes. And when that path is twisted up and stretched and stressed, that's when the energy builds up, and that's when these explosive releases can occur. And that is at the heart of space weather. And we're going to have talks today about space weather. So let me give you just a brief overview. And we have to begin at the Earth, because that's where we're feeling the space weather, because we live in the outer atmosphere of our sun. And magnetized plasma, protons, and electrons are constantly streaming past us in the form of the solar wind. And sometimes that wind can be gusty. There can be periods of stronger magnetic field, stronger density, stronger velocity. But luckily, we have our own magnetic field, which acts as a shield. It's shown here, with our North Pole and our South Pole, forming a shield that blocks the worst of this solar wind that could affect us. Unfortunately, sometimes that shield can break. And in particular, when the solar wind, when the storm that comes from the sun, has a magnetic field which is oriented just so that it will break that of the shield in front of us, it can basically cause a reconnection, a driving, a squeezing of the back, the magnetotail, where magnetic energy has already been built up because of the solar wind dragging the Earth's magnetic outfield out behind it. And this energy then that it taps into can in turn drive geomagnetic processes, including aurora that you see here in the auroral oval. Now, aurora, of course, are another thing that humans have seen for a very long time again. And this is because, it's notable, of course, for its possibility for extreme beauty, as in this photograph. But now, in the last 100 years, 150 years or so, there's a potential for danger that really wasn't there before we were a technological society. Danger to our power grids, danger to our satellites, danger to our astronauts, danger to our navigation, our communication. And space weather is a lot like terrestrial weather in that, just like every day there's weather, and every season there's a particular kind of weather. You have rainy seasons, etc. You can have relatively ordinary season that everybody's going to see in their lifetime. And if you're lucky enough to be an astronaut in the space station and looking out the window, you see that kind of weather in the form of the aurora that happen commonly, especially when there's a lot of solar activity. But just like there are Hurricane Katrinas and superstorms in terrestrial weather, there can be superstorms in space weather. And the so-called Carrington event, which happened in 1859, I was reminded that actually today is the anniversary. It was September 1st that the actual flare that was observed on the sun before the Carrington event was seen, and about 18 hours later that the coronal mass ejection, which we'll see more of in a moment, the storm reached the Earth and drove magnificent aurora. Now, this particular painting is a painting from that era. It's 1865. If you pretend for a moment, and this isn't true, but pretend for a moment that this island is Hawaii, you'll get a sense of what the Carrington event was like, because usually you only see aurora in the polar regions. During the Carrington event, there are auroras down to Hawaii, to Cuba, to equatorial regions. So we have to be prepared for space weather, both in terms of the inconveniences that we're going to face, no matter what, and routinely, and in terms of the superstorms, in terms of the extreme events, which eventually we will have to face as a technological society. Now let's go back to the sun, because this is in fact where the space weather is coming from, where it's originating. This particular movie is a composite of observations. You can see the sun there at the center, and around it you're seeing the solar corona, its extended atmosphere. And you can see the solar wind streaming outwards, and you can see these gusts, these so-called coronal mass ejections, or CMEs. I practiced this talk with my son last night, and I was referring to CMEs without defining them, and he thought I was talking about Siamese cats. So I'm sure I won't be saying coronal mass ejections, I'll be saying CMEs, but not cats, but solar storms. And this is what they are. They're basically huge explosions of mass that travel outwards from the sun at speeds of upwards of 1 million miles an hour. The flare here, this flash of light, can happen, and that light gets to us in just about 8.5 minutes. And the way to think about this, just like in a terrestrial storm, you have rain, you have wind, you have different manifestations of the storm. The same is true in a solar storm. You have the manifestation of the release of radiation, which is the solar flare, and you have the manifestation of the release of mass, which takes about 18 hours, as I've said, or on a very fast one, or maybe 3 days for a slower CME to reach the Earth and drive the geomagnetic activity. So where does the magnetic energy come from that drives these storms? And the answer is inside the sun. And we have various models of what goes on inside the sun. Some of them are better than others. This particular one explains why it rises and sets. Yeah. But it's maybe not the best model. Probably more edifying model is this one. And the short answer to where the energy comes from is from the nuclear fusion at the core of the sun here. And this energy is released in the form of heat and light, and it moves through this part of the sun, which is called the radiation zone. But a photon moving through the radiation zone, although it moves at the speed of light, has a tortured path to follow because it's very dense. And so it's like a pinball in a pinball machine. It's constantly bouncing around. And in fact, it takes a photon about a million years just to get to the surface of the sun. Before it gets there and comes out in what we see as the photosphere, the surface of the sun, invisible light, it has to go through this zone, the convection zone. And this is an interesting zone because this is where the dance of the magnetic dynamo plays out. And let me just briefly give you a sense of the steps of that dance. Because there are motions, and what's happening here is that the energy is now in the form of motion, and that energy then gets translated into magnetism. The convection, the churning like when you put soup on a hot plate on the stove, the moving where it goes up and then it turns over and goes down. This is the convection, and this serves to create the magnetic fields, to magnify the magnetic fields. And then, as these magnetic fields may be pushed downwards, there's a shear layer at the surface between the radiative zone and the convection zone called the tachocline, which stretches the field and amplifies it still more. And when the magnetic field gets strong enough, the plasma entrained in it becomes buoyant, and it rises like a hot air balloon to the surface. And that's this third step of the dance seen here. And as it pokes out through the surface, those are the sunspots, the very strong, focused field that comes out through the surface of the sun. And then there are these motions that are happening, slow motions which are happening, circulations. The surface of the sun is not rotating like a solid body. It's faster at the equator than at the poles. You have those motions, and you have circulations. You have meridional circulations going up and down deep into the sun and back again. And so all together, we have convection, shear, buoyancy, circulations, which are all motions that somehow combine into a dance that creates a magnetic field, and more than that, creates a magnetic field that cycles. So every 11 years, you have more sunspots and more magnetic activity, and then it wanes, and then it waxes again. And I'll come back to that later. That's the brief version of the dance, and you'll hear more in Yuri Tumri's talk next. Will you be dancing for us, Yuri? Of course. Excellent. When it pokes to the surface and we see the sunspots, we can actually observe it. We can measure these magnetic fields. We see it as positive and negative polarity, white and black, the field poking up, and we can see it with tremendous resolution in space and in time. This is at the surface of the sun. The thing is, the magnetic energy that gets built up in the corona and drives these solar storms is built up in the solar atmosphere. So we would really like to know what's happening in the magnetic fields of the solar atmosphere. And to be able to observe that, to make the same observations of positive and negative magnetic field, it takes telescopes that don't exist yet. Luckily, the DKIST is being built, and it will allow us to observe these magnetic fields in the solar atmosphere. And the COSMO, which I'll talk about tomorrow, is a telescope for looking at the global magnetic fields in the corona. But until that time, we have this surface boundary condition, which gives us some information. And we have something else. Because the plasma is entrained, it's forced to move along the magnetic field, we can actually see it in a very real sense. This is an eclipse photo. This is another thing that humans have been observing since there have been humans. And what I want to show you here is a model of what we think the magnetic field looked like in the solar atmosphere on this day. And then these are magnetic field lines. They're just telling you the path of the magnetic field. And I think you can see, I hope you can see, that even some of these structures where it's bright, where you have these closed structures, we can see structures like that in the eclipse image. But of course, this is a two-dimensional projection of something. And what we learn more and more is that magnetism in the corona does not live in flat land. It is a three-dimensional and a twisted concept. There are those magnetic fields that are wrapping around each other, and we can get a sense of that from the dynamics of what's going on in the corona. We can see plasma moving around, twisting around itself, and we can see it erupting, and when it erupts, unwinding. So the twisted magnetic fields are clearly at the core of how and why the magnetic field gets energized. And just to summarize then, in terms of space weather, in one slide, if I have to, what's going on. We have magnetic field, which is stored in twisted, stressed magnetic field. It's then released through an eruption and hurled outwards. That whole twisted structure full of plasma goes out through the solar wind until it reaches the Earth, where, depending on how it's oriented, it may cause extreme impact in our geomagnetic field and in various other technological capabilities. Now, of course, the interesting part is at the boundaries, going from here to here, what happens there? Going from here to here, what happens there? But this is just a snapshot of the picture from end to end. And that's space weather. So how about space climate? Well, it's, again, analogous to terrestrial weather and climate. Just when you want to know when there's going to be, if there's going to be a hurricane tomorrow, you also want to know if next year is going to be a stormy year. If we're going into a time period when we're going to have a consistent drought, for example. We need to know the climate, the long-term variation of space weather, in the same way we need to know the long-term variation of weather. And we know there is long-term variation because we have one of the nicest records in astronomy of the solar sunspot cycle. And I believe some of you, if those of you yesterday would have seen Masumi show this slide, the so-called butterfly diagram, which we have the original of upstairs. Let me first look at this. These are two versions of the same information with a little bit more information folded in here. If you just go out and start counting sunspots, and then you plot them versus time, you get this. And you have to do it for a while. You have to do it for 100 years or so or more to really see that there is a periodic behavior. You go through a time period with very few sunspots to a lot of sunspots and back again about every 11 years. And notice that some cycles have more sunspots than other cycles. The 11-year periodic behavior is really interesting. It's not exact. It's not like exactly the same every single time, but it's close in these periods shown here, which is really very interesting. This is the same information with a little bit more information. Now when you count your sunspots, you also find out where on the sun they appear. And so if they appear near the poles, they're here at the higher latitudes, and if they appear at the equator, they're down here. And now we notice something else, that at the beginning of the sunspot cycle, when they start to appear, they appear at the higher latitudes. They emerge at higher latitudes, and then they go away. And then later, the next ones that emerge will emerge at a lower latitude, and so on, until the butterfly has unfurled its wings. And so this variation over 11 years, over hundreds of years, is at the heart of the space climate. And you may ask, what does this mean in terms of the solar activity, the coronal mass ejections, the flares? Well, again, this shows you the corona, because the corona you can observe in the short wavelengths, in the extreme ultraviolet. And when you see a sunspot on the sun, what you see there in the extreme ultraviolet is a bright region. And this bright region is called an active region. And here at solar maximum, lots of sunspots, lots of these bright regions, and, not coincidentally, lots of flares, lots of CMEs. And as we move around now to the beginning and the end of the cycle, solar minimum, you see that it's dark. And I'll come back to this point in a moment, that it's darker at solar minimum. It's also, there are fewer sunspots, fewer active regions. If I made a plot of CMEs versus time, it would pretty much follow that sunspot cycle plot. And this has an influence not just in terms of solar activity, but in terms of the structure of the solar wind in the heliosphere, this atmosphere that we're embedded in. Let me take a moment to explain this slide. At solar minimum, when there's not very many sunspots, the sun basically has a simple magnetic structure. It has a north pole and a south pole. And it makes this kind of dipole configuration, the same thing you'd get if you had a bar magnet and you put iron filings, it would make lobes, two big lobes. And the plasma gets trapped there, so it's dark here and bright here. When you move out into the solar wind, there's an equally simple pattern that comes along, which is that you get fast wind coming out of that open field here, and slow and variable wind here at the equator. And that's what these plots are showing. Further away means fast. Red and blue here means positive and negative magnetic field. Fast forward 5 or 6 years, and now you're looking at solar maximum. And now you've got sunspots all over the sun, and you no longer have that simple dipole configuration. You have a complicated structure with fast and slow wind, positive and negative wind at all latitudes. It's a much more complicated heliosphere that our Earth is embedded in. And this is a nice movie to visualize this. Focus on this top image and this movie. Don't worry too much about these. This is just showing you 11 years. This is sunspot data, so you're going from minimum to maximum and back down to minimum. And this is a model of the heliospheric solar system magnetic field. And when you have positive field and negative field, what happens is it gets stretched out, so you end up with a current sheet. And that's what this gray thing is. And at solar minimum, when it's very simple, a dipole, that gray sheet is pretty much flat. Here, so we have basically just a dipolar type magnetic field. The color here is velocity. So you have fast wind coming out of the pole and at solar minimum, and slow wind at the equator at solar minimum. But when you get complicated at solar maximum, as we'll see again in a moment, suddenly it's all mixed up. And this means, as you start to get into the structured time of the heliosphere, you get red blobs, the fast speed, coming out from you from the sun. And so you get fast wind forcing the Earth, which is another source of geomagnetic activity. So there are two things going on. There's the flares, the CMEs, that are constantly driving the Earth's geospace, but there's also the structure of the heliosphere. And so let's take it to the Earth and see what this means. At the Earth, now what we're looking at are sunspots in the yellow plot, which are waxing and waning with about 11 years, about 100 years of data. And the red is now showing you the Earth's response in terms of the measured magnetic field of the Earth. And you can see that at first sight, yes, it follows very well, because when there's a lot of coronal mass ejections, there's a lot of sunspots, there's a lot of coronal mass ejections. When there's a lot of coronal mass ejections, there's a lot of geomagnetic activity. But there's some complexity which is associated with the structure of the heliosphere and these fast driving streams. So space weather varies with the solar cycle, and space climate then varies with the way the solar cycle itself varies. And it's not just all about the sunspots and the flares. It's not just all about the active times. Because when we get to the Earth, let's talk about radiation. How much does this variation matter to the Earth in terms of radiation? And we're going to hear a talk this afternoon by Kevin Trenberth, I believe, on this. The biggest input to the Earth's climate system is the sun's radiation. But the total solar radiation actually does not change very much at all with the sun's cycle. It's measurable. This is total solar irradiance over 3 solar cycles. You can see it's going up and down. But if you take a look at these numbers, this is a 0.1% change. It's a very small change, a very subtle change from minimum to maximum in the total solar irradiance driving the Earth's climate. If you start going to shorter wavelengths, though, things get quite interesting. If you look in the extreme ultraviolet, now remember back to that picture I showed with the solar cycle, with the solar maximum, lots of active regions, then it got very dark. It's a factor of 2 difference from minimum to maximum in terms of how much light is coming out in the extreme ultraviolet. And this is interesting because the Earth's upper atmosphere is very sensitive to these shorter wavelengths. And this is seen very nicely in the Earth's neutral atmosphere, the thermosphere. And the thermosphere varies with the solar cycle, and now we're talking a factor of 10 change from maximum to minimum. And now we can see something else interesting. We can see that the depth of the minimum itself might change. And the one in 2008 and 2009 was a lower thermospheric density than any other we've measured. And that's interesting, and you'll hear a talk from Dolores Knipp this afternoon about this, because the density of the thermosphere affects how satellites orbit. And our satellite is filled with, Earth's atmosphere is filled with satellite. Each one of those orange dots represents a satellite. And we need to be able to track their orbits so they don't slam into each other and cause damage or danger for any poor astronauts who might be abandoned in space at the time. This is the killer space junk that was the subject of a recent Science Channel special. So we care not just about when it's active, but when it's quiet. And when it's quiet, during that 2009 ultra-quiet minimum, the radiation belts, which is where the relativistic electrons get accelerated, was very, very quiet. There wasn't any there were no fast solar wind streams and CMEs driving it and filling it. But the galactic cosmic rays, which care about structure and activity and how strong the shield of the sun's magnetic field is, and to how many of them can come in and reach us at Earth, actually reached an all-time high. And galactic cosmic rays are not a problem for us here on Earth because we have the Earth's atmosphere to protect us, but for an astronaut going through space, they are a big problem. And for this reason, for an astronaut on a mission to Mars, they might actually prefer to travel during solar maximum, where there are a lot of flares, but where they can have a warning and shield themselves, or a deep solar minimum, when the galactic cosmic rays have an easy input and access to them. And so space climate is more than just about the sunspots. And so let me just finish up by referring back to that minimum. And was it a weird minimum? What do we mean by an unusual solar minimum? We've only been observing 3 or 4 in the space age. And in fact, if you go back 100 years and you look at things like the sunspot number and the geomagnetic activity, you find that that 2008, 2009 solar minimum was probably about the same as the one about 100 years ago. So it was unusual, but it was not as unusual as the so-called Maunder minimum, which was in the 17th century, where for about 60 years, there were very, very few sunspots at all. And I think we're going to have a talk on that also this afternoon from Tom Woods. So let me conclude by saying that what we have learned about magnetism in terms of space weather and space climate is really the same message we got just by looking around here on Earth and our experience with magnetism at home. What's true at home is true across the solar system and the universe. The magnet is alive, the magnet is useful, and the magnet can be dangerous. And this is because magnetism is a force of nature. It's neither good nor evil, but it's a power that cannot be ignored. Thank you.
Thank you very much, Sarah. We have time for 1 or 2 questions at most, so if anybody in the audience is awake enough to start it rolling. Yes.
This is a simple one for you. You said that the CME plot pretty much follows a sunspot occurrence. Could you explain what the not pretty much part of that is? To a layperson.
I was probably being too weak in my statement. If you plot coronal mass ejections against sunspot number, they're following, well, no, I'll take that back. There's a pretty much element because CMEs don't always come from these active regions. Sometimes you can have a slow buildup over weeks where you build energy up into regions which don't show up as sunspots and they don't show up as active regions, and yet they can explode in coronal mass ejections. So there's not a one-to-one correlation between coronal mass ejections and the sunspots or the activity. However, the origin of those so-called quiescent prominences, for example, ultimately come from the sunspots. So it's a delayed effect, but so its origin is still the magnetism that came from the sunspots, but it's not a one-to-one correspondence.
Any other quick questions? Yes.
So your talk today and some of the things that were mentioned yesterday look at how the effect of these storms have on technology. And I was wondering if you scientists are thinking at all about partnering with the biological sciences to look at the effects of this on life forms, which I think is a very fascinating aspect.
It's a fascinating aspect. We are lucky here on Earth in that we have the Earth's atmosphere, which really shields us from the worst biological effects. And that's why, over the centuries, space weather was not a danger to humans. It's really more a danger to our technology here on Earth. The exception are the astronauts, or possibly very high altitude people who spend a lot of time in high altitudes, airline pilots and the like. But for astronauts going to Mars, it's a huge effect, and quite likely, the solution is not going to be, is going to have to be a biological solution rather than because we can't stop the cosmic rays.
Right, let's thank Sarah again for a wonderful talk.